Welcome to the 365 Days of Astronomy podcast. I'm Maurice Kemp, amateur astronomer. There are an interesting host of celestial bodies and objects that exist on the opposite side of the Earth's atmosphere from where we stand. Celestial bodies such as the Sun, the nearest star and governing body of our solar system, the Moon, the Earth's only natural satellite, the stars, point sources of light that allow man to navigate beyond his line of sight, and wandering stars, the planets that captures man's curiosity because of their seemingly irregular paths, all of which serve to drive man's desire to learn more about the world beyond the reach of everything, to include his naked eye. Everything except for his imagination. Long before early man's imagination began to truly focus on the nature of the stars, his view of them was unknowingly distorted. He had no idea that his naked eye, which was subject to the Earth's atmosphere, could only accommodate the apparently largest and brightest stars in his night sky. And so he would have only been able to count 2,000 to 3,000 of the 200 billion stars that made up the Milky Way, our galaxy. With civilization, a few men had the opportunity to pay closer attention to the stars. They took note of their seemingly fixed arrangements, the pattern of their movements in the skies over time, and their general appearance. Their improved understanding of the stars helped to develop their concept of time and their understanding of seasonal changes. In search for the origins and meaning of life, man imaginatively associated constellations with their gods, people, and animals of their stories and myth. Today, most of the naming conventions for stars and constellations that have survived are of Arabic, Greek, and Roman origin. Historically, the heavens fed the imagination of men and provided them clarity about the nature of the world around them, not realizing that the clarity of celestial bodies and objects depended on atmospheric conditions and the limits of their naked eye. Celestial bodies vary in brightness. The brightest celestial body is our Sun, followed by the Moon. The naked eye is unable to detect light if it's too dim. And a much dimmer example of a celestial object is the Andromeda galaxy, and one of the dimmest bodies detectable by the naked eye is Uranus. To uniformly categorize the apparent brightness of celestial objects, a scale was formalized based on the star Vega, which expresses units of brightness in magnitude. Vega itself has an apparent magnitude of 0, brighter objects are negative and dimmer objects are positive. Our Sun has an apparent magnitude of -27, and our full moon has an apparent magnitude of -12. The faintest or dimmest light detectable by the human eye is approximately -6 magnitude under optimal conditions, where you have near perfect darkness or very little ambient background light. The Stargazing atmosphere is structured in 5 principal layers and is held in place by our planet's gravity. It serves the purpose of moderating extreme temperature changes between day and night, absorbs UV radiation, and provides us the essential warmth for life through the greenhouse effect, allowing light to pass while trapping the heat that radiates from the Earth's surface. The 5 structural layers of our atmosphere are the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is dynamic and plays a major role in protecting life on our planet. The dynamics of these layers also impact electromagnetic radiation to include light. Our atmosphere dynamically scatters, refracts, transmits, absorbs, and reflects the light of celestial bodies that travels through it en route to our eyes. Dynamic scatter results in our skies changing colors from sunrise to sunset, and dynamic refraction of our atmosphere is why celestial bodies such as planets blur and stars appear to twinkle. And astronomical seeing defines the blurring and twinkling of celestial bodies, such as stars, caused by turbulent mixing in the Earth's atmosphere, which is a phenomenon that varies its optical refracting index. The astronomical seeing conditions vary from time to time and with location. The astronomical seeing is expressed as seeing this and is measured in arc seconds. Optimal seeing provides the lowest measure of arc seconds per possible, such as 0.5 arc seconds, and this is achievable at locations such as the Mauna Kea, a location that is high, dry, and cold, and that is potentially very dark. The challenge of viewing celestial bodies and objects beyond the scope of the naked eye was met 400 years ago. In 1608, Hans Lippershey paired a concave and convex lens to form the first crude telescope. In 1609, Galileo Galilei is given credit for demonstrating its usefulness in the world of astronomy. Observing celestial bodies on the opposite side of our atmosphere, and with the aid of his plano-convex, plano-concave telescope, revealed details undetectable by the naked eye. In particular, Galileo's observation of the planet Jupiter yielded an unimaginable discovery. On the 7th of January of 1610, Galileo observed Jupiter was flanked by a straight line of small bodies. Continued observations revealed the bodies were moving toward and away from Jupiter. On the 13th of January, Galileo observed a fourth body. Galileo then concluded that the four bodies were moons orbiting Jupiter. In March of 1610, Galileo published a pamphlet titled Sidereus Nuncius, in which he revealed the details of his revolutionary observations. 400 years of evolution shaped that telescope into an amazing tool. What started as two pieces of refracting glass that crudely focused light to multiple focal points depending on the wavelength of light served as the inspiration for the parabolic planar mirror telescope that reflected and focused light. This reflecting telescope was designed by Scottish astronomer James Gregory in 1663, and the first model was built by Sir Isaac Newton in 1688. Both telescopes produced unique forms of optical aberrations, and both aberrations were correctable to a certain degree. Whether it was the chromatic aberration of the refracting telescope or the coma aberration of the reflecting telescope, both telescopes improved the range of celestial bodies that can be observed by the naked eye. Both telescopes were subject to size limitations, though. Rigid optics had upper size limits due to their tendency to deform under their own weight. But as industry and technology improved, the telescopes were built larger and larger to collect more and more light to observe wider ranges of celestial bodies. Another innovation displaced the human eye altogether, one of the original limiting factors. It was displaced by the camera. This took place in 1880. This allowed for long exposure images, an idea introduced by astrophotographer John Draper, and this allowed for very low light that made very faint celestial bodies and objects viewable for the first time. The improved telescopes were still subject to the astronomical seeing of our atmosphere. The first efforts to reduce astronomical seeing was to reduce the amount of light passing through it by viewing space from a much higher altitude. The Hooker telescope, which first saw light in November of 1917, was the first to apply the solution of large optics and high altitude to improve our image of celestial bodies and objects. Other notable telescopes are the 200-inch Hale telescope in California, the 6-meter BTA-6 in the Caucasus Mountains in Russia, the 10-meter Keck-1 in Hawaii, and the 10.4 Gran Telescopio Canarias on the island of Las Palmas in the Spanish Canary Islands. Adaptive optics are also used to correct for atmospheric seeing, along with reducing the amount of atmosphere between us and the celestial body by setting up telescopes at higher altitudes. The most impressive effort to eliminate atmospheric seeing was to put telescope in space. And in April of 1990, less than 400 years after the first telescope, the Hubble Space Telescope was carried into space by the Space Shuttle Discovery on mission STS-31, where it was placed in near-Earth orbit. With an orbit period of about 96 to 97 minutes, the Hubble Space Telescope employs amazing technologies to capture still images of celestial bodies and are designed to be serviced in orbit. The Hubble Telescope has been serviced 5 times and is expected to remain in orbit until 2014. 4 years after it leaves orbit, the Hubble Telescope is scheduled to be replaced by the James Webb Space Telescope, which is designed to orbit for 5 years with a goal of 10. The James Webb Space Telescope will provide incredible images of space using 3 anastigmat photographic lenses. I am Maurice Kemp, an amateur astronomer and space enthusiast, and I hope that as our view of our amazing universe grows clearer and clearer, so will our understanding of it as well as of each other. Thank you for listening to my podcast. Goodbye for now.